is create conditions in that anaerobic zone that favor the PAOs to be the only ones that can get to that VFA, right? So it's Michael, right? Yeah. So he had a question about this a little bit, and I pointed something out to him that again we're these are PAOs, right? Or heterotrophs. Sorry, they're both right. These PAOs are heterotrophs. And so heterotrophs, like a normal heterotroph, right? Just like the ones that Paul talked about a lot that make up the bulk of our bacteria, right? They take that VFA in, they grow on it instantly, right? They're just using oxygen right away. Whereas our PAOs are taking that VFA, they're storing it, and then they're utilizing it. But what they're also doing is they shuttle a little bit of the energy that's available from the stored carbon has to go to making these poly Ps, right? Nothing in life is free. So like 10 or 15% of like the overall energy available from this VFA that comes into a PAO has to get shuttled into making that poly P, which means their growth rate is just a little bit lower than a normal heterotroph. Lower growth rates, right? What that means, if we talk in these lower growth rate terms, it just means they're slower, right? They're not as fast. They're not going to win a competition under certain conditions, right? And so when we think about our anaerobic conditions, the only way that PAOs have an advantage is if they're the only one that can access this VFA. If you put them in a condition, right, where there's oxygen or nitrate available, they're going to lose to our normal heterotrophs because they don't get as much energy, right? So it's not so much that the anaerobic condition is something special that like the PAOs just really need to be swimming around under anaerobic. The important piece of it, the reason that anaerobic condition is important is because it means there's no oxygen and no nitrate, because our PAOs can't compete for the carbon with normal heterotrophs if there's either of those two things around. Right? So it's the anaerobic conditions are the indicator that you created the conditions where only the PAOs can go after the VFA. That's what the anaerobic conditions mean. So that's why we're trying to create this, because without that, these guys don't have the competitive advantage. They're not going to win. If you just have aerobic conditions, the PAOs aren't going to grow because they actually don't get as much energy from the carbon, right? So you put a heterotroph and a PAO next to each other, you put them in aerobic conditions, hey, maybe a PAO grows a little bit, but the heterotroph grows 15% faster.
This ought to work. This will work fine because I'm going to go downstairs in a little bit.
And then, okay, so the growth, what does that 15% faster means? It means that after a week, there's 10 times as many heterotrophs as PAOs, right? After a week and a half, there's 100 times as many heterotrophs as PAOs. It's just a growth condition, right? So if you seeded your basin with a 50-50 mixture of PAO and heterotrophs, and it's all aerobic, it's not that the heterotrophs die under aerobic conditions. I'm sorry, it's not that man, I'm doing bad with mixing my stuff up. I'm confusing the hell out of you guys today. It's not that the PAOs die under aerobic conditions. It's just that the heterotrophs outcompete them and grow faster and multiply faster. And so you just wash them out. But when you put that anaerobic condition in, the heterotrophs can't access the VFA. And even though the PAOs get less energy from that VFA, they're the only ones that can access it, right? So we're kind of like coddling them along, right? Yes. Sure. Mm-hmm. Yeah, no, that's a great question. So I'll ask the cruise operator, like the guys out. You're in the environmental compliance. Is that?
Yeah.
Yeah. Okay. So you're not out in the aeration basins doing operations. Okay. So I'm just going to connect with you. Liquids operators. When glycol comes in, what are you worried about? You worry about phosphorus removal? You do worry about phosphorus removal?
Well, no, not phosphorus removal. What I'm worried about being upset.
Upset, and what are your indicators of upset? Air demand? That's what it is. So it's a great question on what glycol does. PAOs and heterotrophs, like whatever, they might at a high enough glycol concentration, right? They'll be impacted. But what really controls the glycol limits at wastewater treatment facilities, and particularly crews, is the impact on nitrification. So stuff we talked about yesterday, those AOB, and it kind of goes along the same rounds though, right? So we're talking about energetics and like favorability of growth and competition. And we talk about heterotrophs and then these PAOs like, 15% slower. Like those nitrifiers are like 30% as a fish. So it's like 70% slower. So they really need to be coddled. And they become very sensitive. So when they get kind of any kind of inhibitory impact, like they're not as robust as a heterotroph or as a PAO. And so that's why we watch glycol, because it'll impact all those nitrification processes we were talking about yesterday. And glycol, are you seeing the glycogen? And maybe that's what's triggering it. So glycogen is a very different compound than glycol. Yeah. It's an inhibitory compound. And so it's more like they're, and I honestly, I can't think exactly how it impacts them from an inhibitory standpoint, but inhibitory compounds can impact like cell wall structure. It can interfere with some enzymes. It's more that it's not glycol is not a competition impactor. It's an inhibitory impactor. Yeah. That makes sense?
Yes.
All right. What are you going to say, Mike?
I think a real good example of that is 2018 when SDMHA come in. Wiped out. Basically, the LPs totally wiped out. Phosphorus part of the plant, VAOs. I didn't.
Is glycol not a carbon source?
It's a carbon source, but it's harder to break down, right? It's like, like we can eat hamburgers, but we can't eat grass, right? But they're kind of made of the same thing at the end of the day. Yeah.
You wouldn't have a problem.
Not with glycol. Yeah, it's a very different structure compound. It's yeah, I mean that's why they use it for de-icing and stuff, right? It'd be great if they sprayed like acetate to de-ice, and that's what came into the plant. You can handle that, but glycol it's just a chemical compound, and it's different than glycogen. Yeah, good question. No, that was great.
It's not that much chemistry.
Yeah, it can be broken down. It's just slower. It's like a bigger chain, like more complex compound than a volatile fatty acid, right? And it's not going to come into play. The PAOs will see it and be like, I can't even try to do that, right? So, because again, they're energetically just a little bit behind a heterotroph, right? So they need to have the really easy stuff. Like they can't deal with these big complex chains and big complex compounds. There's a solution, right? So at cruise they limit the amount that. So do you know where it comes from? Does anybody know where glycol comes from at cruise? DFW, right? And so they got these big ponds, and essentially environmental compliance helps us set a limit to say you can only send us this much of that, at any one time. And that's what our plant can handle because you have a long enough, it's all about hydraulic retention time. So if cruise had 24-hour HRT in the aeration basins, right, you could take a lot more of it because you'd have enough time to kind of break it down, and it's gonna, that glycol will still slow down some of your rates, right, for your nitrifiers. But if you make your tanks big enough, it'll be okay. But you don't have 24 hours of retention time at cruise, and so then you have to keep the concentration low enough that when it comes into the plant, it gives a level of inhibition that you can deal with. Right, and it's enough time that can be broken down as well, right? So there's a certain mass loading that a certain HRT and biomass can handle, and so it's all just, yeah. They store like, I mean, when do they stop discharging glycol this spring? Have they stopped?
No,
Is
they
it?
don't usually stop at that.
Yeah. So from de-icing in the winter, they stop sending it in August or September. So yeah, it's really spread out. Like it's a lot of storage that they have. Some airports treat it just on site. You can, like, if you want to do glycol treatment, like any compound can be broken down biologically as long as you give the selective pressures and the retention time. And so some airports will build their own treatment system. Some airports actually do glycol recovery even. It's just not at DFW. You guys don't charge them enough, I guess. I don't know.
They shipped it over to Alliance Airport. They started dumping it down the drain to come to Denver.
How'd that work out?
Yeah.
They got you. Yeah, no more travel.
One of the few things I can make kind of super sick of my stuff.
When it was coming in.
I'd rather be able to sense it with my nose than just wag it.
So we tested just to test.
Good questions. All right, where were we now? Let's see. And I don't know where were we at. Please throw stuff like this out. That's what this is all about, right? We don't have to go through the slides. You guys got them for references. Let's see. All right, so anaerobic conditions that what we're having. The thing to remember is the anaerobic conditions. You know what they are. It's not that PAOs can only grow in anaerobic conditions. It's just that's the environment where they have a competitive advantage. So we have to do everything we can to protect that competitive advantage. Otherwise, other organisms will grow and we won't end up with our PAOs. Let's see. AFFF. Oh man, don't measure PFAS when that stuff comes through. Go ahead. How much would it take to impact a plant this size? Boy.
Evolution.
What left will you take at a plant? Like, what's your
0.
0? There you go. 0, Steve. Thanks, Paul.
You're welcome. Glad I could answer something.
It's EVPR instability. So glycol doesn't necessarily. AFFF might. Like, I don't know. It might. Paul said you shouldn't have any of it, so we shouldn't even talk about its instability impacts. So we're managing our competition in our anaerobic zone. I'm going to give another angle for it. This is an analogy I've used before. I know Rodell really likes it, so we just keep using it year after year. So what is VFA? So again, when you're thinking about, all right, we're trying to keep this competitive advantage for our PAOs. You know, what we want to give them is the volatile fatty acids. And we talk about volatile fatty acids a lot, and really that's like the best piece of our wastewater. It's the best fraction, right? So this is the part Rodell likes. So it's like the bratwurst, right? All right, everybody likes to eat bratwurst. That's what you get. You call me fat one day, Rodell. I'm just gonna keep piling it on. All right, so everybody likes brat. Like, I'm from Wisconsin, so I have to, like, yeah. That's like what the VFAs are. You know, everybody wants to eat it. Everybody wants access to it. But what we want to do is make sure that these PAOs get access to it. And again, they're not the most energetic. They're not like the top of the line, you know, like performance athlete. They're a little slower, right? So they got to be coddled a little bit, right? So when you put those VFAs into our wastewater, and if you just add them into the head end of the aeration basin, you know, what we're really talking about is the energetics, and they have to be paired with something, right? right? You can't just eat a brat. Like, you need to drink something with it or consume something with it, right? So when we think about the chain of what our bacteria prefer, right? When I eat a brat, I like a really good like good beer, right? A good full-bodied lager. That's like oxygen, right? If it's there, you get your brat. So we have brat fries. Do you know what a brat fry is? No. So a brat fry is in Wisconsin. When you go like to the grocery store on the weekends, there's a little brat stand, and like all the different community groups, right? The Boy Scouts, Girl Scouts, 4-H, they do brat fries, which just means they have like a big grill and they're cooking brats, and you just walk up, and you buy a brat out of the stand to like eat while you grocery shop or eat while you go home. And then there's a cooler next door to it, right? So all right, you get your brat, you walk over and you open the cooler, and if there's a good beer, you grab the good beer, right? That's the first choice. That's oxygen for our bacterial population. If there's oxygen available, they're going to grab that out of the cooler. All right, but then it's like, okay, well, all right, you open the cooler, and it's like, oh, it must be kind of discount week at the brat fry. And there's only like light beer, like a Bud Light or something, right? You're like, okay. I guess it's all right. It still tastes okay with my brat. But it's not quite as good. But if nitrate's there, they're still going to use it. These are still kind of a cut above oxygen and nitrate. All right, then if you open the cooler and maybe it's more of a church group, and there's only water, not Catholic church, so I'm Catholic and we drink a lot. Yeah, we have a drinking problem in our state. Yeah, it's I mean, I like it. I don't know if everybody, I lived in Texas for a while, and I remember the first wedding I went to here, and I got there and there was like no alcohol, and I was like, what is going on here? Because like in Wisconsin, like it's a party. Okay, I thought everyone, I was blown away by this. There were a lot of guns. That was not surprising, but the alcohol was. So I don't know. All right. So anyways, then you open it up and there's water. And you say, okay, I've got the brat. I guess I'll do water. That's the EBPR metabolism, right? It's kind of the bottom of the choices for bacteria because of the energetics, right? So we have to really kind of, just in a completely unregulated, right, supply of everything, EBPR would never happen, right? So front of 10 mile, there's no selector zone, EBPR doesn't happen because it's the water, but there's all kinds of beer available, right? So we have to do everything we can to make sure that our bacteria don't have access to these other things and just focus on the water, right? If you eliminate these, we know they'll still do it, but they're going to be tempted, right? They're going to be tempted if there's any beer in that zone. All right, so that's what we do. We put in mixers, right? We put in mixers at the front of our basin, so there's no oxygen transfer. That's a simple one, right? You just take your diffusers out, put in mixers. That's what so Mountain Creek just went through this, right? We're in the process of doing it. And you just don't have aeration. Well, I guess you had surface area. Anyway, you just put some mixers up front. All right, well, the next important part then is to make sure you denitrify. Right, so like when we had the blankets up there before, if you're denitrifying in your blanket and get a little nitrate there, you're helping to eliminate that kind of temptation for the bacteria, and they just go after the PAOs. But otherwise, you have to have something in your process configuration to get rid of the nitrate in the RAS before it comes back to the head of the basin. Right now, if there's plenty of brats, right? If there's like if there's 4 brat stands, right, and there's only 2 coolers, you can have all kinds of Bud Light and water. People are still going to take the water because they don't want to wait in line for the beer, right? So the more brats you have, the easier it becomes to manage these competition, because if there's all kinds of brats, there's enough for the guys to have their Bud Lights, and there's enough for them to have water too. Or that's not the right way to say it. People are going to stop waiting in line for the Bud Light and they'll go get the water, right? The PAOs will still grow if there's plenty of this VFA available. And that's why you see differences in complexity in BNR configurations, right? So when we just do some kind of this theory, we get a lot of different ways to put in biological nutrient removal and activated sludge plants. So like this one, there's anaerobic condition at the front end of the basin, and then it's just aerobic. Right, and they get biological phosphorus removal. What plant does this remind anyone of? Cruise, right? Probably Mountain Creek too, right?
Yeah, that's a,
So what do you think about if you put in this configuration where you just have this little zone up front, right? Are there a lot of brats or not a lot of brats in that influent? Anyone? Yeah, there's a lot, right? There's plenty to go around. There may be some nitrate in your RAS, but it's okay because there's enough to go around, right? There's plenty of brats to go everywhere. Let's look at this configuration. This light's driving me nuts. So I'm gonna mess with it a little bit. That's still okay? How about that? If it just stays. All right, how about this one? So now we have this anaerobic condition, and then there's this anoxic condition, right? And there's a mixed liquor recycle pump, we call it, that's bringing the nitrified mixed liquor back into this zone, and it's kind of wrapping around here. And the RAS comes right into the front end of the anaerobic zone. So this anoxic zone is trying to denitrify this whole like chunk here, right? It's bringing some nitrate back around and trying to chew that up in the anoxic condition, right? And then recycling it back around, trying to bring your overall nitrate down so there's not nitrate to compete with in the head of the plant. So this is decruise setup, right? So if you have a little bit fewer brats, you kind of go to this configuration, and you're trying to knock the nitrate down here. What are we consuming the nitrates with in that anoxic zone downstream of the anaerobic zone? How do we get rid of nitrate? Like what are we pairing with nitrate? Let's move away from my broad analogy. It's just BOD, right? Yeah. BOD, nitrate, it gets removed. Essentially here you're using the other pieces of BOD. So you're trying to get your PAOs to kind of get their fill of brats. And then you have the brats that are left over, and maybe like side salad, that's available in the anoxic zone. Right? And that's what you denitrify with, the leftovers and the stuff that, you don't want to eat as much as the brat. And then you get your aerobic conditions for nitrification. Right? So if there's plenty of brats, we can be very simple because there's plenty to go around. As we start to get limited, we need to have some anoxic conditions downstream of the anaerobic zone. And we do the denitrification with the leftover BOD. Right? We're still kind of prioritizing BOD for our PAOs. You have other configurations. I won't spend a lot of time on these. That just like have the less. What I want to emphasize with these is that the less VFA you have in the influent, right? The less ideal your influent wastewater characteristics are to biological phosphorus removal, the more complex your BNR configuration is going to get. Right. So the Clean Water Services example I had, where I said they were very carbon limited, they have 10 different zones along the length of their aeration basins with walls and mixers and diffusers, because they have to be very precise in where they add their RAS and where they add their VFAs in, because it's a very limited resource. Like that carbon is the limited resource for a biological nutrient removal facility, and we can't be wasteful with it, right? Unless we're like independently wealthy and our collection system gives us 110 milligrams per liter of VFAs, then we can be a little sloppy. But as you bring that down, you just have to have these more complex reactor configurations to really just dial in that carbon addition for PAOs, right? And make sure you have ideal conditions for them to grow in. I always throw this picture up here. It's an aerial, but we've been doing this for a while, right? So it started in 1974 was the first full-scale BioP plant. So it's not like BioP is just something that we thought up a couple weeks ago. But what we do know now is we understand it much better, and we can dial in our bioreactor configuration. And I think what's going to be interesting over the coming decade at TRA is that as nutrient removal regulations come to all the facilities, every facility is going to have a slightly different BNR configuration, right? And a little bit different operating strategy. And the reason is, so why would that be? Why is every plant going to have a little bit different BNR configuration and a little bit different operational strategies? Yeah, different loading, different characteristics. Yeah, it's, you know, it used to be everybody had a big tank and you aerated it, right? But depending on your loadings and your wastewater characteristics, right, you may have to have a more or less complex bioreactor configuration to achieve the same effluent performance, right? And you know, so environmental compliance, are you in the lab? Is that kind of lab work, or is that just like, I was trying to make a connection with sampling, right? Does that fall under y'all? So what you see at Cruise is there's a lot of sampling that goes on to characterize the influent BOD and COD, right? RBC, like that flock and filtered COD, soluble COD. You get these requests from me and Eric, like, oh, can you do more of this data? Well, this is why it's important, because that carbon fractionation, the type of VFA you have coming in, really determines how you need to operate your wastewater plant to hit effluent phosphorus numbers, right? So it all kind of trickles around, is that, you know, understanding your wastewater characteristics is what really determines how you implement BioP and how stable performance is going to be. Well, we're at 10 a.m. and I'm only a quarter way through. Let's do cruise or decruise. Then we'll take our break. All right, so let's talk about some plant profiles. See what's happening, and if it goes really fast, then maybe we'll do cruise right away before break as well. So this is actually a couple of years ago already, where there was a bunch of sampling done out at decruise. So it's been more than 2.5 years. So no one from decruise is actually like in the room that was here when the sampling was done anymore. I don't think. Everybody's been shifted around. It's probably fair. And so what they did is they were having some you know, stability questions and performance questions. I gotta turn the lights down again. No, it's from all the way off. But how's that? Everybody okay with that? Yeah. All right. So here's their bioreactor configuration. So you've got this kind of splitter structure here where RAS and influent kind of mix together and then split to 2 aeration basins, right? That flow goes into an anaerobic zone. So this dark one is anaerobic, right? Then they've got that anoxic zone, right? So remember that configuration we just looked at. And then here's that mixed liquor recycle pump. So it's pumping from the back end of the plant into this anoxic zone. And then you've got this blue aerobic zone, right? So why are we pumping here? Like, what's the point of having that pump be in place? What are we pumping from the back end of the plant into the anoxic zone? I'm getting old, I think, here as well. Nitrate. Nitrate, yeah. So you're trying to bring in, right? So because in this aerobic zone, the nitrifying bacteria are taking our ammonium to nitrate, but there's no BOD left back here, right? So we need to kind of pump a bunch of them back up here to where the BOD is. Right, and this flow rate, that flow rate is in the 200 to 300% of the influent flow. Right, so if you have 5 mgd of influent flow coming to this basin, this mixed liquor recycle pump is pumping at 15 mgd. Right now, it's a very low head pump. So what's the, have you seen the pump at all in your 2.5 years at the decruise? I don't know the picture there, but it's like a window fan, you know, like those box fans that you put in your window. It's open. What were the flows again? So if you have, I don't think it's actually 5 mgd. I'll just make my math easier. 5 mgd coming in, this would be pumping 15 mgd. Yeah, 2 to 3 times. Okay. Okay, so then it'd be at 7.5 mgd. Right? Yeah. I don't know if that's exactly where you're operating at, but it's around there. Like 2 to 3 times the flow rate is typical design. Maybe it's listed in here even. No, it's not listed. But it's like a big ceiling fan or a box fan in your window on a pipe, because you're not pumping against a lot of head. That's the thing. Like when you're pushing from here to here, it's not like you're lifting the water up a lot, right? Like you think of a pump station, like your RAS pumps, like you're lifting that water out of a well back to the head of the aeration basin, right? You're lifting it up feet. Like here, you're like, it's like an inch. So you're really just pumping against like the head loss in the pipe. So it's not a huge horsepower, right? I say that just as you start to see other BNR configurations, you're like, oh my gosh, 15 WD, I got to pump that much. You do, but it's very low horsepower. That's probably only like 20 horsepower pump. It's not a massive pump. All right, so what they did is say, okay, well, let's do some measurements in our basin. So we look at the DO and nitrate at the very beginning of the anaerobic zone. Like, why would you measure DO and nitrate at the beginning of the anaerobic zone? What are you trying to verify with those two measurements?
They're eliminated.
Yeah, why do you want to be eliminated? Yeah, you're getting rid of all of your liquor and making sure there's just water available to pair with the brats. All right, so that's what they did there. Then they went through the anaerobic conditions and then measured OP, orthophosphate, so soluble phosphorus. Why did they measure soluble phosphorus at the end of the anaerobic zone? Exactly, you're making sure that PHA is being stored and the phosphorus is being released. All right, now we come through here. There is another pump in place right here. John left. We could ask him if it's ever been actually operated. It's not operated right now, so just ignore that. Now we get to this little spot, nitrate, ORP, and OP. So why are we measuring nitrate at the end of the anoxic zone? Yeah, you're trying to see how much denitrification you had here, right? If this nitrate number is really high, leaving the anoxic zone, what does that tell you? If there could be some oxygen, what else could happen if there's nitrate leaving the zone? Not an inhibitor. Go along the same lines of the oxygen. What do you need to remove nitrate? Yeah.
Enough PHA?
It could be PHA. Keep going. What is it? The BOD, right? There's got to be enough BOD to do denitrification. If you have nitrate leaving your anoxic zone, it means you had more nitrate than BOD. Okay. Well, as an operator, what might you do if there's a lot of like nitrate leaving the zone?
Hold back your circulation.
Yeah. Why not turn this down? Like you're bringing back more nitrate than you can denitrify. You're just kind of, you're pushing your bacteria harder. Like you're recycling them around. It's not really doing you any good. So typically we like to see like a 1 or 2 milligram per liter nitrate leaving the anoxic zone. It means you brought enough back that it's fully denitrifying. What if that nitrate is like 0? What if you don't measure nitrate at the end of your anoxic zone? Yeah. In what condition are you going to be in then if there's 0 nitrate? All right. So we have no oxygen, no nitrate. And what condition do we then have? Anaerobic condition. Yeah. Anaerobic, right? So we don't, we've got plenty of anaerobic time, so we don't really want to be going anaerobic in an anoxic zone. We want to be denitrifying as much as possible. Right? If there's no nitrate left over, it could be that there's some BOD left over, and we don't really want that to go to the aerobic zone necessarily. And so then you would push your pump up. So there is an ORP controller on this mixed liquor recycle pump at Cruise or D-Cruise. Boy, did we talk ORP yesterday?
No.
No, let's just not even talk about it today. That'll be another 45 minutes if we talk ORP. And then they measure the OP. What do you want to see with the OP at the end of an anoxic zone? What do you think is going to happen to the orthophosphate, right? So you release it all here, right? What could be happening to orthophosphorus when you get through the anoxic zone? Yeah, because we talked about oxygen as being what PAOs use to grow with PHA, but they're okay with nitrate too, right? They're not beer snobs. They're okay with a little bit of Bud Light, and they'll actually do that growth with PHA under anoxic conditions, right? So you don't necessarily want to see your OP increase across the anoxic zones. You want to see it decrease. All right, then you get to the aerobic conditions. DO and ammonium in a bunch of spots. Why are we measuring DO and ammonium as we go through the anoxic conditions? Or aerobic conditions? Exactly. Make sure you're nitrifying, right? See how much nitrate you're producing. And then they added in the orthophosphate profile. What is that? What is like this orthophosphate number going to tell us? Yeah, and how it's gonna. What do we want to see here? So we've gone through anoxic and aerobic conditions. What's going to happen to that phosphorus condition by the time you're into that aerobic condition? What do you want to see happen? Yeah, like you want them to be taking that poly P up and growing as fast as they can. You want them to be consuming their PHA and storing their phosphorus. And then just kind of going through the back end of the plant and then just getting to the very end. And this is essentially your effluent, right? All right, so this can give us a sense of like, oh, what happens as we go along the length of our aeration basins. All right, so let's look at some profiles. So here's the DO. So you look at these numbers and it's like, oh, well, my DO is not 0 in my anaerobic zones. What does that make you think when you see these really low DO numbers in an anaerobic zone? Yeah, if you're measuring, so how do we measure DO? The probe. You stick a probe in and it tells you 0.1. What do you think? It lowers up.
It's working.
Yeah, it's working. So this is our anaerobic zone. And you're like, oh, I'm going to see if I have any DO in my anaerobic zone. Was that? No, you're fine. It's been a long few days. So I can't keep anything straight either. So don't feel bad. Okay, so when you go out and stick a DO sensor into the anaerobic zone and it measures 0.1, don't overreact. Like you're probably getting to the limit of measurement accuracy of that sensor, right? So, it's like, oh, okay, there's a little bit, but that's probably just sensor error. And then when you get to the oxic zone, yeah, they're in that 3 to 4 range, okay? And then it's very high DO of the rest of the basin. So you know what, it got up quickly. So with decrews, they needed this. They needed to be able to get their DOs up very rapidly. What they did see though, so this is one of the aeration basins and the parallel aeration basin. Do these look exactly the same? No. So there are different growth pressures for DO between these two basins. And you'll see this in, depending on the level of control and the level of kind of distributed drop legs and control valves, this is pretty common, right? To see not the same DO profile in parallel aeration basins. All right, so DO, that's DO. That's not unexpected. What about ammonium and nitrate? All right, so remember we're anaerobic, we're anoxic. Again, the blue dots are nitrate. Oh man, we measured a little bit of nitrate in the anaerobic zone. If you see like a 0.2 or a 0.3 nitrate when you do a measurement in an anaerobic zone, what do you think? Are you worried? If that number was real, would you be worried?
Yes.
Yes. But maybe you don't believe that, again, everything gets down to like your limit of detection. And when you're using like hop kits, getting below a 1 on a nitrate, it's not, you're kind of getting below their limit of accuracy, right? So if you go out and do these tests, just always be thinking about limited detection. What am I actually measuring? All right, then we see our ammonium. By the time you get through that first aerobic chunk of the aeration basin, the ammonium's already down to 2.5. Right? By the time you're to the oxic 3, it's all gone. All right, so if we go back to the process flow diagram, oops. 1, 2, 3. So by the time you get here, the ammonium's completely gone. All right, that means that this is just safety factor at the back end, which is not bad, but that's what it is. Now, what about nitrate? Yeah, but look how low that is, right? This is saying that your effluent nitrate is only going to be 1 or 2 milligrams per liter, maybe like 5 or 6 milligrams per liter. What's going to happen to the RAS in that clarifier blanket if there's only 6 milligrams per liter of nitrate in your mixed liquor? What's that? Yeah, it's going to go anaerobic in the blanket. Right, so you've got to really be managing that blanket then and thinking about how long the blanket's sitting in there and trying to get it out. The lower the nitrate, right, kind of the less flexibility you have in like building up a sludge blanket. Yeah. Yep, because because why? Why does low nitrate mean your sludge blanket's going to go anaerobic faster? Not nitrify. Put two letters in front of that nitrify. There we go. Going to denitrify. There's less nitrate to get rid of before it goes anaerobic, and that could be a good or bad thing, right? But it's just something to be aware of, that if you see changes in your sludge blanket dynamics, check out the nitrate concentration in your mixed liquor, right? And take that into consideration when you're targeting your sludge blanket thickness. What about orthophosphate? So we only did 2 measurements there. In the anaerobic zone, ortho P is 15 to 20 milligrams per liter. All right, so you're going to see a very high release number in your anaerobic zone. In the effluent, you're at 0.3 and 0.75, right? So you're getting really good uptake. I'm not sure what happened to our point that was in here. Like that must not have actually happened like we wanted it to. But you're getting very good uptake, right? You've got good release and good uptake, and you're really managing that nitrate and the ammonium in different ways in the profile. So that's one bioreactor configuration, right? Multiple zones, mixed liquor recycle pumps, and you get really good effluent phosphorus. Cruise is a very different BNR configuration, and it's been an hour, so we'll